Hi everyone. So today we're going to continue our discussion on standard form of a plane. So we come up to this formula on last video. So I want to point out several things that are important about this formula. So number one, notes. Okay, notes. First thing I want to notice is that the coefficients, which we talked about in the last video at the end, but I didn't get to write it down, so I want to write it down for you guys. The coefficients of x, y, and z basically form the perpendicular vector. As a matter of fact, the advantage of standard form is that you can read off the perpendicular vector directly from the standard form, which is one of the reasons why it's called the standard form, because of the fact that the perpendicular vector is so easily accessible. And we're going to be using the perpendicular vector for different things. 2. The value, the constant d, is basically the dot product between the perpendicular vector and any point on the plane. And yes, any point. So if every single one of you in the classroom right now, or in every one of your classmates will pick a different point on the plane and dot product with the perpendicular vector, all of you have the same exact answer. As a matter of fact, this value d is what determines whether a point is on the line or not, combining with the perpendicular vector. That's the significance of it. Now, show you how to form the standard form of a plane. So, of course, the most basic and easiest question I can ask you to do is that if I give you everything, you need to do it. So find the equation. So notice the word equation, so not parametric representation, of the plane that is perpendicular to the vector 1, -1, 3, and contains the point -2, 5, 4. So this is a very straightforward problem because I gave you the two things that you need to do the problem: the perpendicular vector and the point. So go ahead and let's do this. So here is my perpendicular vector, which is 1, -1, 3. And then the point that we have is, I'm going to call it vector x sub 0, which is -2, 5, 4. Important to identify these two things correctly, because otherwise you mess up your problem. So now all I have to do is the following. So this would be my A, this would be my B, this would be my C. And then to find D, D would be the dot product between these two things. So that would be 1, -1, 3, dot product -2, 5, 4. And so therefore come out to be, let's see, -2, -5, would be -8, and then -2, -5, -7, plus 3 times 4 is 12, so 12 and -7 is 5. There you go. And so what is my equation of the plane? Would be 1x, which I'm just going to write x, plus -1y, which I'm just going to write -y, plus 3z equal to 5. So that would be my plane. Pretty simple. Now, of course, you might be thinking like, well, what if I didn't give you everything you need to write the equation of the plane? How would you do that? Well, you won't be able to do that yet. The problem here is that the perpendicular vector is essential to forming the standard form of a plane. But if you think about it, you really have no way to find perpendicular vector yet. Oh, I know, you're thinking like, well, can we look at the dot product between equals 0? Yes, you can, but that requires you to be given the vector to begin with. So if you're not given the perpendicular vector, then you really don't have any way to find the perpendicular vector yet. We will talk about how to do that in 1.6. So therefore, it's coming. Okay, remember, I cannot show you everything in one day. So you're going to have to slowly learn some of this stuff. So now, next thing I want to show you is the following. Now that we have this equation of a plane, so this is what we call standard form. Standard form equation of a plane. What if now I ask you to do this? What if I ask you to now rewrite this equation, x minus y plus 3z equal to 5, into parametric form, into parametric representation? Now, why do we want to do that? Well, parametric representation has its advantages because it identifies some direction vector that will allow us to actually use if we want to define some kind of coordinate basis system on the plane. Okay, if you think about it, the way we define a plane using parametric form is actually nothing more than coordinate basis, where vector u1 and u2 are basically the basis, and t1, t2 are basically the coordinates. So therefore, it does have its important usage. Okay. However, the parametric form is good for something else. The standard form is good for some other things. That's why you need to learn both of them and be able to kind of comfortable with both of them. So if we do have an equation, how do I write it into parametric form? Well, it requires the same technique you know how to do with the line. So when you're given a standard form of a line, what is one way for you to write in parametric form? Well, there are multiple ways to do it. One way will require you to rotate the perpendicular vector that you got from the standard form into the direction. Then you can just simply use that and just pick any one point on the line to do it. The problem that method does not work in this case because we don't have a rotation 90 degrees in R3. See, in R2, we can say rotate around the origin on the plane, on the XY plane. But in R3, you now can rotate in infinitely many directions. So therefore, that method is not going to work. However, a much simpler method would work, and that would be simply create perimeters. And if you recall, when we talk about it, when we did that with line, I told you that the easiest way to create a parameter and to rewrite an equation into parametric form is to let the independent variable be the parameter. The problem here is that it's not going to work with a plane because we have too many variables. But is that a surprise that we have too many variables? No, if you just think about the course, the title of this course, you should know that is going to be the case. So show you how to do this. So the way to do that is to realize the following. You have a plane, an equation of a plane. If I were to write it into standard parametric form, we call in parametric form, this plane has two parameters, t1 and t2. And therefore imply that when we have to create parameter to rewrite this equation into parametric form, I have to do two of them. So this is how you can do this problem. The first thing I'm going to do, I'm going to go ahead and solve for one of the variables in this equation. So the easiest one to do, I'm going to go ahead and solve for x. So x will equal to y minus 3z plus 5. And then what I'm going to do, I'm going to create my parameters. I'm going to let y equal to t1, z equal to t2. Yes, you need two of them. Reason, because a plane is two-dimensional. It's a two-dimensional object. And therefore, require two parameters when we write it in parametric form. So how do I write in parametric form? This is how. Just simply line things up and make sure you put things in order. In parametric form, we want to define three equations, x, y, z. How do I define these three equations? The first equation is y minus 3z equal to 5, but we don't use y and z. We use our parameter. t1 minus 3t2 plus 5. What is y? Y is t1. What is z? Z is T2, but notice where I put T2. I lined up with the T2. Now here's the important part, is to learn how to fill in the missing information so you can actually write in parametric form. When you say T1, that means 1 T1. 1 T1. Notice that Z doesn't require T1. So what does that tell me? 0 T1. Just like with the line, we don't like subtraction because we want to define position in vector form using vector addition. I'm going to go and change that to plus negative 3 T2. Notice Y doesn't have a T2. I'm going to say plus 0 T2. And then this has a T2, so I'm going to say plus 1 T2. And Y doesn't have a constant at the end. I'm going to put in 0. And Z also doesn't have a constant. I'm going to put in 0. And now all you have to do is group things together. If I group these numbers together, these numbers together, these numbers together, now all of a sudden I have vectors. So this just turned into the following. Vector x, y, z, which is basically what vector x is equal to T1 times 1, 1, 0 plus T2 times negative 3, 0, 1 plus 5, 0, 0. That becomes the parametric representation of the plane in R3. Now, just like all parametric representation, is this the only parametric representation of a plane? The answer is no. There are plenty. There are infinitely many. Okay? So what I do want to show you is, what if we redo this entire process, but instead of letting y and z be t1, t2, we do, I don't know, x and z instead? Well, let's find out. Let's say I take this equation, x minus y plus 3z equal to 5. I'm going to solve for y. So then I'm going to move y over, and y would equal to x plus 3z minus 5. Because I moved the y to this side and then move the 5 over. Now what I'm going to do is I'm going to let x equal to t1 and y, z equal to t2. So what will happen to my parametric representation? Well, let's see. X, y, z. X would equal to t1. Y would equal to t1 plus 3 t2 minus 5. And z would equal to t2. Once again, learn to fill in the information that's missing. 1, 1, 0, t1 plus 0, t2 plus 1, t2 plus 0 plus 0. And now group things together. Okay, this is my vector x. This is my first direction vector, second direction vector. Oh, and here minus 5 become plus negative 5. See, when you form the vector, you have to have all the same plus sign. That's why it's important to make it into plus and then negative. So what is our parametric representation in this case? Well, it will be vector x is equal to t1 times 1, 1, 0 plus t2 times 0, 3, 1 plus 0, negative 5, 0. Now, one thing I do want to illustrate with these two parametric forms is the following. It's something that we talked about last week. Remember I told you last week that two planes can be parallel. It is possible for two planes to be parallel without any of the direction vector being multiple of each other. And these two parametric representations illustrate that perfectly. Because these two parametric representations represent the same plane. By definition, a plane must be parallel to itself. So therefore, these two parametric representations represent two planes that are parallel. But notice the direction vector. Yes, these two direction vectors are multiple of each other, but these two are definitely not. And yet they're parallel. One of the many reasons why it is not a good idea to determine if two planes are parallel by looking at the direction vectors, because you won't be able to determine that at all. So don't try. Now, of course, then the question is, how do you know if two planes are parallel then? Well, we'll get to that, don't worry. What I'm going to ask you to do is the following. The last thing I want you to do is, what if you solve for z instead and find the parametric representation? What would you get? Okay, and I'm going to go and write down the answer for you so you can try it out and see. So this is what would happen if you let solve for z and let x and y be t1, t2. Then you have this parametric form. All right, so you can definitely check your answer once you're done and make sure that you got it right. And these are just three of infinitely many parametric representation of a plane. So next thing that I want to talk to you about is the following, which I teased quite a few times already. If you cannot look at the direction vectors of a plane, or between two planes, and determine whether the two planes are parallel, then how would you be able to determine if two planes are parallel? Well, this is how you know. The problem here is that because there are infinitely many direction vectors that you can use for a plane, and therefore there's way too many combinations to consider for you to actually try to figure out if this pair and this pair would actually form a plane, two planes that are parallel. But lucky for us, a plane actually have one unique perpendicular direction, and therefore become a lot more manageable when we use that. So this is what you need to know. How do I know two planes are parallel? Two planes are parallel if their perpendicular vector are the perpendicular vectors are multiples of each other. Notice that is exactly how we determine two lines are parallel. One of the nicest things about this is that when we talk about lines and plane using perpendicular vector, there's very little mathematical difference between how we determine things. Okay, so that's the interesting thing. So this statement is exactly the same if I say two lines are parallel if their perpendicular vectors are multiple. That's exactly the same concept. Then you can probably guess, how do I determine if they are perpendicular planes? Two intersecting planes are perpendicular if the dot products between their perpendicular vector is 0. Notice that is also the same exact thing I wrote for two intersecting lines being perpendicular. Once again, the important part here is to realize that when you talk about perpendicular vectors, a line and a plane follow the same rules. But if you talk about parametric form and the direction vector, then they don't, which is one of the reasons why we like to do things with perpendicular vector. Conceptually easier. Okay, now one thing I also want to point out is the following. If you have two planes in R3, if they are not parallel, they must intercept in R3. In higher dimension, R4 or higher, they are skew planes. Same exact concept with skew line. Two planes that are parallel, that are not parallel, but yet they don't intercept each other. Just like skew line being two lines that are not parallel, but they also don't intercept. So those are possible. And once again, the idea is exactly the same with lines, but just with higher dimension. Now, one last thing I want to point out is this: two planes are the same. That means they're the same planes if they are parallel and have at least one point of intersection. And of course, the idea here is that if they have at least one intersection point and being parallel, they must have infinitely many intersection points. And then the question, then sometimes you wonder, why don't we just say that? Because you don't want to check infinite intersection point. We want to check one intersection point. That's easier to do. That's why the definition here say at least one. So if you do one, then it's good enough. You can do more, but you can just do one. Now, one last thing I want to talk to you about is the following. Notice that when we define this plane using perpendicular vector, the perpendicular vector actually can be any length. As we see in this example right here, we define these two lines using two different perpendicular vector, and they are multiple of each other. But they don't look the same, but they are multiple. Therefore, it forms two planes that are parallel. So the idea here is that, is it possible to kind of have some kind of notation that we can kind of force everyone to use the same exact perpendicular vector, so that it's easier for us to identify planes that are being parallel, because then we don't even have to worry about the multiple part. And of course there is. The idea here is the following: the perpendicular vector is simply used to identify the perpendicular direction. So what if we take away the length that's involved and just simply have the direction? And you might be thinking, then what does it mean by taking away the length? Well, what I mean is, I mean to use a length that doesn't affect the problem. And that is called unit length. So imagine the following. Let's say given an equation of a line or a plane, doesn't matter because they actually kind of same thing, with perpendicular vectors P. What's the difference between a line and a plane in standard form? A line requires perpendicular vector in R2. A plane requires perpendicular vector in R3. And therefore a line exists in R2 because the perpendicular vector is in R2. And if you have a perpendicular vector in R3, then we'll form a plane. Now notice that is also the reason why if you ever try to write me a standard form of a line in R3, it would not be possible, because whatever line that you write, whatever equation you write, would actually represent a plane in R3. And I'll explain that to you in a little bit, but let's finish this part first. So if we want to not worry about the perpendicular vector being different length, we can write what we call the normalized, we can write what we call the normalized, equation of this plane, or this line or plane, by using the normalized perpendicular vector. In this case, I'm going to call the normalized vector n, and n would equal to vector p divided by the length of vector p. So therefore, you can have an original equation, which is vector p dot vector x minus vector x sub 0 equal to 0. And that can be transformed into what we call normalized equation, which would actually be equal to n dot vector x minus vector x sub 0 equal to 0. Or you can think of it this way. Think of it as just 1 over the length of vector p times the original equation. So think about it. If I have this equation, so let's say example, let's say find the normalized equation for, let's say, x minus y plus 3z equal to 5. So how will we do that? Well, simple. We're going to first start by identify the perpendicular vector. Oops. And now all I have to do is find out the length. The length of vector p is equal to square root 1 square plus negative 1 square plus 3 square. And that comes out to be radical 11. So you can think of the normalized perpendicular vector would be 1, negative 1, 3 over radical 11. And what is the normalized equation? Well, the normal equation will be 1 over radical 11 multiplied by x minus y plus 3z equal to 5. And therefore, give me this equation. 1 over radical 11x minus 1 over radical 11y plus 3 over radical 11z equal to 5 over radical 11. Now, yes, I know that equation actually looks kind of yucky compared to the equation that we start with right here. See, this equation have a non-unit perpendicular vector, which is okay in most cases. But in some cases, we might want to have a normalized perpendicular vector, and then this equation will be much better. Okay? Yeah, that doesn't look nice. Now that we talk about standard form of equation, standard form of plane, now I want to talk about the following. See, one of the things that often get confused is the following. Is that if I have an equation in R2 for a line, can I just say that equation would be the same if I put in R3 and also represent a line? The answer is actually it does not. The problem is that when you have an equation, that equation really you need to know what dimension the equation is in so that you know what it represents. Now you might think that's confusing, but it's not. Imagine the following. Imagine I tell you this. Consider the equation right here. Consider the equation x equal to 1. If I ask you to show me the graph of x equal to 1, I would say majority of you will be saying, oh, x equal to 1 is a vertical line. I learned it in 7th grade or 8th grade, or in geometry. When I learned about equation of line, then I know that x equal to constant is a vertical line and y equal to constant is a horizontal line. Right? The answer is wrong. Why is it wrong? Well, technically speaking, it's not wrong, but incomplete. Why is it incomplete? Because x equal to 1 does not necessarily represent a vertical line, but can actually represent the following things in R1. Here's my R1. X equal to 1 represent a point right here. That's in R1. What happened if I now move on to R2? In R2, x equal to 1 is a vertical line, just like what you think. Guess what happened in R3? In R3, x equal to 1 is a plane. It's the same exact equation, represent at least 3 different things in 3 different dimensions. Therefore, important to understand that whatever equation you roll, it has to have some kind of meaning to identify what dimension it's in. And therefore, interesting thing to note is that what if you have an equation like this? Let's say given an equation, x minus 3y equal to 5. What is this thing? Well, guess what? This thing in R2, it is a line with perpendicular vector 1, -3. But what if this exists in R3? In R3, this same exact equation does not represent a line anymore. That's the problem. That's why you can never write me an equation of a line in R3, because whatever equation that you're thinking will very likely represent a plane instead. So why is this represent a plane? It represents a plane because in R3, it is a plane with the equation x minus 3y plus 0z equal to 5. With perpendicular vector 1, -3, 0. So now comes the big question. If I given this equation right here, how do I know what dimension it's in? Well, you really don't. But we can assume the following rules. Number 1, if it say x minus 3y equal to 5, you can assume that it's in R2 because they only have 2 variables, x and y. However, if the problem specifies what dimension is in, then you could theoretically add more 0 times the variable to form a correct, proper perpendicular vector. Like in this case, it would be incorrect for me to say that this is a plane in R3, but define a perpendicular vector that is 1, -3 without the 0 at the end, because that would be incorrect math. So therefore, when you give an equation, it's very important to pay attention to what the problem is describing so that you know what the equation represents. Because if you look at this and think it's a line, but the problem described this has to be in R3, then you just mess up the problem. Because this is a plane in R3, not a line. The geometry is completely off if you think of it as a line, but it is a plane. So keep that in mind. And as I told you last week, now with problems that exist in different dimensions and having an equation in different dimensions have significance, have consequences that you need to consider, you always have to pay attention to that and always ask yourself the questions. What dimension are we working with? Okay, because it's important. All right, I think I'm going to have to stop right here. The video is about 33 minutes. And tomorrow's video will be the last of the 1.5. And we will wrap this up. Hopefully tomorrow's video will be shorter. All right, talk to you guys later. Bye-bye.